Assalamu alaikum. In most linear algebra courses taken by engineers, the matrix is introduced as this box of numbers that you could use to solve systems of linear equations using Gaussian elimination. But this explanation, although it's very simple, really undermines the true power of the matrix and linear algebra. So, in this video, I'll do my best to explain what a matrix actually is. I'm going to define it rigorously, and then we're going to see a bunch of steps used to construct the matrix, and then we're going to derive a formula in order to use it, to use this matrix. So, before I start this video, I have to assume that you know a few basics. You know what a vector space is, what is its dimension, the span of a set, the span and linear independence, a linear combination. You should know all of these concepts before you watch this video for you to actually benefit from it. So let's begin by a quick refresher. First, a mapping or a transformation is said to be linear if and only if it satisfies the linearity property. This property can be split into two smaller ones, that is homogeneity and additivity, but this one does the job. So it basically says the image of the linear combination of a certain bunch of vectors is equal to the linear combination of the images. Okay. The second one is that a basis is defined as a set of vectors that satisfies two properties. First of all, the vectors of that set must be linearly independent, meaning no redundancy, so that the only way to create the zero vector from a linear combination of all of those vectors is by having all of those scalars equal to zero. The second one is the spanning property, and it simply tells you that you can make any vector in that vector space just by linearly combining the vectors of that set. Okay. Okay, so the third one is basically an emphasis on what we've said here. Any vector in the vector space can be written as a linear combination of basis vectors. Okay, now from the first and second properties, we can actually make a very interesting deduction. Notice that, as we said, any vector can be written as a linear combination of the basis vector. So if we select a certain basis, let's call it BV, that is equal to V1 all the way to the n, and then for that vector space, if we take a vector belonging to it, then V can be written as alpha 1 V1 all the way to alpha n Vn, right? Now, if we want, for example, to find the image of this vector, then we could, for example, take its components and plug them directly into the expression of that linear transformation. For example, the transformation T of xy is equal to 5x 3y. This is a certain linear transformation. It scales the components. So I could take the components of this guy, plug them in here, and basically get my transformed vector. But instead of that, I could first transform all of these basis vectors and then find the transformed version by linearly combining those instead. Why does that work? Well, that's because of the linearity property. The linear transformation of V, its image, is equal to the linear transformation of this linear combination, which is equal to alpha 1 LV1 all the way to alpha n LVN, a linear combination of the transformed vectors. So from that we get that the only information we need to find the image of any vector, no matter what, is basically, first of all, its representation in terms of a certain basis. We need these coefficients. We need to write that vector in terms of a certain basis. And then we need the transformed version of the basis vector. So we take that mapping and we feed into it all of the basis vectors we have in that selected input space basis. That's it. That's all the information we need in order to represent a linear transformation. Our goal now is to take that information and represent it compactly in a mathematical construct, in this case, a box of numbers or an array of numbers. Okay, obviously this box of numbers must contain the images of those basis vectors, obviously. Okay, so a matrix is a mathematical construct, an array of numbers used to efficiently represent the linear transformation. Why would you want to do that? Well, we're gonna see the reasons later. Just keep in mind that computers like numbers. Okay, so how to construct a matrix? Well, given a linear transformation that takes us from the vector space Vn over the field F to Vm or Wm over the field F, we can construct its m by n matrix using the following universal steps. Okay, so it takes in vector V, spits out W. So first, select the basis for both the input and output vector spaces. They can be the same if those vector spaces are the same. If not, then you have to choose different ones. And obviously, I recommend you choose the standard basis for both the input and output spaces. It's going to make your life way more easier. The second step is to find the images of the input's selected basis vectors. Basically, take that basis, that set, and transform every single one of those vectors. Very simple. You have to use the definition or that expression of the mapping. Then find the representation of those vectors in terms of the output space as basis. Well, why did we add this third step? Well, because we said these two vector spaces could be different. So, since this vector, this transformed vector W exists in the output space, then we can indeed write it as a linear combination of its basis vectors, the ones that we have selected. And when we obtain those coefficients, we can start building our matrix columns. So, reminder, the last step means basically express the transformed input, input space basis vectors as a linear combination of the output space basis vectors, then write them in column vector notation. So take LV1 and write it as a linear combination. These coefficients you get form your first column. I believe you know how to represent a certain vector in matrix, in column vector notation. You're supposed to know that. And then take the second one, do the same thing, obtain a second set of coefficients, and obtain the second column. Do that until you transform all of the vectors. All right, and then what you're going to do is stack these columns and form your matrix. So you get n columns and m rows. So this is called a column, this is called a row, and each number here is called an entry. For example, this green number here is the ith, is the entry in the ith row and the jth column, where m is the number of columns, a number of rows, and I is the row index, and n is the number of columns, and j is the column index. Hope I did not mess that up. A is the m by n matrix representation of L relative to the bases BV and BW. And obviously, as you might have guessed, if you change these bases, you're going to get a different representation, a different matrix. Let's take an example, a quite tedious example actually. As I told you above, obviously you should choose the standard basis all the time because it makes your life way easier. The representation in that basis is the exact same thing as that vector. You just write it in a column vector. We can do that obviously because we have the input and output spaces are the same vector space. But still, just for the sake of learning, we're going to use this more difficult example. So if I give you these two bases, they span the vectors, their vector spaces, and they are linearly independent, these two vectors. The first step is done. This is the selection. It is already given. The second step is to transform these two vectors of the input space. So T of V1 is T of 1, 1. Basically multiply the y component, you get 1, 2. And then transform the second vector, T of V1, T of V2 is going to be 1 minus 2. Now these two vectors now exist in the output space. You can write them as a linear combination of the output space basis vectors. These two, W1, W2. So that's what we're going to do here. So 1, 2 is equal to A11, W1 plus A21, W2. Now, by solving this system of linear equations, you obtain the two coefficients and hence the first column of the matrix. I suppose you know that, as I said already. So this expression is equivalent to this. So 1 is equal to A11 is equal to 2 A21. And same thing for the second row. Solve your system of equations and do the same thing for the second column vector and get the second matrix column. Now stack these side by side and you get your matrix, this 2 by 2 matrix relative to these two bases. Okay, how do we use this thing now? I mean, we have the information all contained within this box, this array of numbers. How do we use it? Well, to use it, first you must transform a given vector. Sorry, what am I talking about? Using a matrix means transforming a vector using it. So to do that, we must first find the representation of that vector that we have selected in terms of the input space, the selected basis vector. We're going to call it x, and it has coefficients x1, x2, xn. You get by that by solving that system as usual. We can do that for any vector in that vector space because of the third property we've discussed earlier. After transforming it, we're going to get a vector y that is already the representation of w in the in the basis of the output space bw. W is the image of V. So these coefficients you're going to get out of that transformation are already written in the output space spaces. Okay, so now we must find a formula that relates the components of y to those of x and the entries of a, i.e., write yi as a function of the coefficients of the input vector and the entries of the matrix Aij. So here we represent the linear transformation L by the matrix A, and the vector V is represented by X and W is represented by Y. Okay, and L of V, the application of L on V, the calculation of the image of V using L, this operation here is represented by another operation that we define right now. We call it matrix vector multiplication. We can define it once we find this equation here. So let's begin the derivation. So starting from first principle, the first equation, L of V equal to W, if and only if L of the linear combination composing V equals by linearity is equal to the linear combination of the transformed basis vectors. This works for any vector in that vector space. And as you can see, the entire derivation relies upon this property holding. If it doesn't hold, then there's no matrix. It doesn't make to talk about the matrix of a transformation if it's not linear. All right, so now we're going to do the same thing for W. We're going to write it as a linear combination of basis vectors of that space. And then we're going to also expand L of V1. Remember, L of V1 can be written as a linear combination of the output space basis vectors because it belongs there. And it is, and these coefficients are indeed just the entries of the matrix. So expand all of these vectors, and then you can distribute your x over all of them. So now what we're going to do is try to group all of the terms that are multiplied by W1 and then those multiplied by W2. So for example, you get x1, a11, W1, and then x2, a12, W1, and so on until the last component right here. No, not here, right here. So do that for W2 and Wm and group them, pull W2 and Wm as a common factor. Then for this equation to hold, this implies that these coefficients must be equal to y1 and this coefficient must be equal to y2 and so on. So by setting the coefficients equal to each other, we obtain y1 equal to x1 a11 plus x2 a12 and so on, and y2 equal to that other sum. This looks quite like a dot product, doesn't it? We're going to talk about that later, but now notice that the only thing that is iterating in this first row is the index of the coefficients of the input vector and the column index of those matrix entries. So we have x1 of a11 and xj of a1j and so on. For example, here we have xj of amj plus xj of amj and so on. So from that we can deduce that yi for any component I is equal to the sum, you say dot product, of xj aij. Quite interesting. J iterates from 1 to n, the number of columns, and I ranges from 1 all the way to m, the number of columns. Okay, this formula, although it's not that difficult, would still not, I prefer not to memorize it. We want to derive an even simpler formula for us to use on paper for hand calculations. This formula will be left for computers. We're going to use this, we're going to program a computer to calculate using this formula. Now, let's rewrite this set of equations differently. Remember that this can be written as a vector, right? These are components of a vector. It's a vector equation. So we have this vector, y, it's exactly what we're looking for. It's equal to this other vector by pulling x1 as a common factor plus x2 as a common factor times the second one, and so on. You can also notice that these vectors are basically the columns of the matrix, right? So from that, we also derive that y, the output vector, is a linear combination of the columns of the input vector, the columns of the matrix, sorry. So it's xj, aj. This is what matrix vector multiplication is defined to be. This is how to apply and extract the information inside of a matrix. Okay, now I want to simplify even further. I'm going to make this formula so easy to remember by introducing this mnemonic formula. Mnemonic formula is basically just an easy way to memorize certain steps of a certain operation. This formula is not rigorous, obviously, because a dot product is defined to operate on two vectors. In this case, you can clearly see that this is not a vector, this is a matrix, and these columns, these entries here, are not scalars. They are vectors themselves, column vectors to be exact. But still, it does indeed look like a dot product. I mean, x1 times a1 plus a2 x2. This is very easy to memorize. So this vector right here is exactly our input vector, but it is just flipped. So y is equal to ax is equal to a dot ax transpose, where dot is the familiar dot product that we all know and love in, for example, physics. X transpose transposition is an operation where your columns become your rows and your rows become your columns. It is the flipped input vector. You rotate it just counterclockwise. So, for example, the components of the input vector we had are x1 all the way to xn. If you transpose it, then you're going to get x1 all the way to xn. The first column becomes the first row. It becomes a row vector instead of a column vector. I think you can easily memorize that. Let's see an example. Find the image of this vector using the matrix A. Matrix A that we have derived earlier for that linear transformation. So X is equal to the representation of V in the basis BV, right? We can find these coefficients simply by solving this system of equations. We have 7 over 2 minus a half. And then y, our vector that we're looking for, is simply going to be equal to the matrix vector multiplication of a and x. It's this one here. And then using our formula, we can take this dot product, a1 times 7 over 2 minus a2 times 1/2. I think you know how to take this product. So you have 7 over 2 minus 1/2 times 5 over 2. This is the first entry. And the second one, this goes with 0. And minus 1/2 times 4 over 3 is equal to minus 2 over 3. Now this vector, as I told you, is written in the basis of the output space that we have selected. Now, if we want to remove this basis and write it in terms of the standard basis, we simply use the defining equation. We have W is equal to L of V equals to Y1 W1 plus Y2 W2. It's equal to a linear combination, as I said, but in this case, the coefficients are known. We're actually just looking for the coefficients of this vector here. So by calculating this using a calculator, we get W is equal to 3, 8. This is exactly what you expect from that linear transformation, as we have defined it as x to y. You have just multiplied 4 by 2 and got 8. You might think that this is absolutely ridiculous. Why do all of this work if I could just multiply that number with 2? Well, in this case, as I told you, we have chosen a very tedious example. These input and output space bases could have easily been chosen as the standard basis, where when you try to find that representation, you don't have to solve any systems of equations, you just rewrite those entries in that column vector. Also, this is a very small matrix. Usually, for example, in simulators or numerical solvers, you have huge matrices, maybe like 10,000 by 10,000 matrix. You're definitely not going to do that by hand, especially if it was like a function or the expression. So instead, we program a computer to calculate it for us using this formula. Also, as I told you earlier, that computers like numbers. What I meant by that is it's a lot simpler to write a program, for example, in C++, where you first store an array of numbers, n by n array of numbers, no matter how big it is, and then define a certain operation using operator overloading that does this or uses this formula. You can define two objects to be two matrices and multiply them instantly using a computer. So this is one of the main advantages of matrices. We're going to see a lot more of these advantages once we advance a bit in matrix algebra. Okay, thank you for watching. That's all that I have for now, and see you next time.